Hey guys. This is Space Train. Your daily express till the edge of the space. And today we will talk about what is time dilation. Grab your tickets and let's go. Don't forget to subscribe to get unlimited pass on our expedition. Time never seems to do what we want it to. There never seems to be enough of it when we're late for work or school, but far too much of it when we have to stand in the pouring rain waiting for a bus. These annoyances apart, it seems that time flows along smoothly, never bending, never changing its rate, always on time. This steady flow is so reliable that we fit our lives around it. We start the day when the clock tells us to, work when it tells us to, eat when it tells us to, and go to bed when it tells us to. Time, it seems, is constant. That the flow of time is constant is seemingly obvious, and this has been the prevailing view for almost all of human history. Sir Isaac Newton, when he wasn't dodging falling apples, certainly thought time was constant. He gave us the idea of a clockwork universe, in which it would be possible to know not only all of the past but all of the future if only we could say where every particle was, in what direction each particle was moving and at what speed. This model assumed, not unreasonably, that time flows at a never-constant rate. As brilliant as Newton was, he was, much to everyone's surprise, wrong. We take for granted that time ticks by at the same rate for everyone. But Einstein's special theory of relativity shows that this assumption is not strictly true. In 1905 Albert Einstein published his special theory of relativity. This work considered time not as a single constantly flowing entity, but as part of a much more complex system, linked with that of space itself. This is called space-time. Because space and time are part of the same entity, it's impossible to move in space without moving in time. Time, for anything moving, changes. One of the most startling consequences of special relativity is that any moving clock slows down relative to a stationary observer. There are of course many different types of clock, such as digital watches, clockwork clocks, atomic clocks and even our own biological clocks, but they are all equally affected by the same principle, namely, moving clocks run slow. According to the theory of relativity, time dilation is a difference in the elapsed time measured by two observers, either due to a velocity difference relative to each other, or by being differently situated relative to a gravitational field. As a result of the nature of spacetime, a clock that is moving relative to an observer will be measured to tick slower than a clock that is at rest in the observer's own frame of reference. A clock that is under the influence of a stronger gravitational field than an observer's will also be measured to tick slower than the observer's own clock. How slow do clocks run? A reasonable question at this point is, if moving clocks run slowly, why don't we notice? There are two reasons for this. We are going far too slowly for any noticeable change to take place. And even if we go at high enough speeds to bring about a large slowing down of local time, we wouldn't notice because our own body clocks would also be running just as slowly. The speed of light is very close to 300,000 kilometers per second, 186,300 miles per second. It isn't until we get to speeds that are a large fraction of the speed of light that any change in the flow of time becomes apparent. However, at speeds very close to that of light the effect grows in magnitude very rapidly indeed until time almost comes to a standstill. So, when we move, at whatever speed, time slows down relative to a stationary observer. But note that, for example, the occupants of a rocket traveling at very high speeds would still experience time passing normally. However, if they could see out to an earthbound clock, it would appear, to them, to be running too quickly. If an earthbound observer could see a clock inside the rocket, it would appear to be running too slowly. This is why the theory is called relativity. It is because time is relative to whoever is observing it at a particular speed. One question often asked about relativity is what would happen if we went faster than light? It's sometimes said that time would run backwards. Special relativity tells us that this is simply not possible. The universe has a speed limit of just under the speed of light, and it has a clever way of stopping us from breaking it. As we go faster, our apparent mass, as measured by an external observer, increases in proportion to our speed. In fact, our mass seems to increase at the same rate as time slows down. We know from everyday experience that the heavier an object is, the more energy is needed to move it. If we try to move an object at 0% of the speed of light, we will find that it has the mass we expect it to have. However, the mass of the object will appear to increase in ever-increasing proportion to our speed. For example, at 99.5% of the speed of light, the object will weigh around 10 times what it did when it was stationary. As our speed goes ever higher, so the apparent mass increases, and so does the energy required to move it. At the speed of light, it would take infinite energy to move any mass. Since it's clearly impossible to obtain infinite energy, we can never quite reach the speed of light, but we can get as close as our energy supply, and technology, will allow. Note that the occupants of any rocket traveling at very high speeds will not be aware of any increase in mass, just as they wouldn't be aware in any change in the rate that time passes. It's only when they measure the mass of stationary observers that they will see that there has been a change in mass. The astronauts will perceive that everything around them and their rocket has changed its mass while their own seems to have remained constant. There is, however, something that can travel at the speed of light. Is light. A closely related phenomenon predicted by special relativity is the so-called twin paradox. We will talk about this in our next video. But now, how we know it works. The time dilation effect predicted by special relativity has been accurately confirmed by observations of the increased lifetime of unstable elementary particles traveling at nearly the speed of light. Such time dilation has been repeatedly demonstrated, for instance by small disparities in a pair of atomic clocks after one of them is sent on a space trip, or by clocks on the space shuttle running slightly slower than reference clocks on Earth, or clocks on GPS and Galileo satellites running slightly faster. Time dilation has also been the subject of science fiction works, as it technically provides the means for forward time travel. The latter experiments, furthermore, have confirmed a gravitational contribution to time dilation, as predicted by the theory of general relativity. We know, this idea that strange things happen as you near the speed of light. There are strange changes to the length of things, bizarre shifting of wavelengths. And most puzzling of all, there's the concept of dilation, how you can literally experience more or less time based on how fast you're traveling compared to someone else. And even stranger than that, as we saw in the movie Interstellar, just spending time near a very massive object, like a black hole, can cause these same relativistic effects. Honestly, it's enough to give you a massive headache. Maybe one day we will build some machine that can move more than the speed of light. Or find ways to go near large gravitation fields and survive. Just do not give up on this idea, and one day maybe we can go on expeditions through time. There are lots of questions left, so don't space out, and leave some space in your brain for answers. I hope you enjoyed this video. If you want to see more, subscribe and click the bell button, to get notifications on our latest videos. If you are still here, grab your knowledge and get out of my train.